All right, so to wrap up our discussion of graphing polynomial functions, we're going to take a look at kind of the most important theorem of algebra, and that is the fundamental theorem of algebra. I say kind of because depending on what you're working on, really the theorem that you're using at the time is most important. But overall, the fundamental theorem of algebra says if p of x is a polynomial function of degree n is greater than or equal to 1, and the polynomial equals 0 at n roots, where n could be a multiple root or a complex root or just a plain old rational root. And then we're going to take a look at an example here. Let's find the roots of f of x. So why don't you go ahead and pause the video and finish copying down the fundamental theorem of algebra and the examples, and then we'll dive right in. Okay, so here we go. Let's find the roots of, or the zeros of, this function f of x. The first thing I'm going to do is I'm going to think about, well, what are all of my possibilities? My possible rational roots, Here I'm using the theorem from the other day where we're using the possible rational root theorem. The possible rational roots are going to be plus or minus 1, 2, and 4, which are all of these guys right here, all of the possible factors of 4, divided by plus or minus 1, which would be all of the factors of the number 1, which in this case is just 1. So our options are positive 1, negative 1, positive 2, negative 2, positive 4, and negative 4. Let's just be brave and try something. I'm going to start with 1. I don't know, I'm feeling good about 1. If I plug in 1 into synthetic division, then these are my coefficients, and I drop it like it's hot, and then I multiply and add, multiply and add, multiply and add, multiply and add, multiply, and then yes, woohoo! You want to get a remainder of 0. Remember that if you get a remainder of 0, then you have indeed found one of the roots, one of the zeros. Now I'm going to kind of take over where I left off using the same kind of breakdown. What am I feeling lucky about now? How about negative 1? So drop it like it's hot. Multiply, add, multiply, add, multiply, add. Now this time I came up with negative 6, which is a nope, that didn't work. Bummer. So let's try something else. So negative 1 was not it. How about if we try 2? I guess 2 is kind of next in line in our list of possible rational roots. Now I'm going back to my most recent success, which is going to be 1, 0, negative 3, 0, negative 4. So make sure that, so like this line right here is going back to right here. Save yourself some time. Go back to the most recent depressed polynomial. Okay, so then I drop, and I multiply and add, multiply, add, multiply, add, multiply, add. 2 times 2 is 4. I end up with 0. Yes. Woohoo! So I found another 0. X is equal to 2. I am 2 down and I have 3 to go. Oh, bummer. 3 to go because I have an x to the 5th leading me off, which means the fundamental theorem of algebra says I better end up with 5 zeros. So my depressed polynomial at this point is 1, 2, 1, 2, or gosh, what would that be? Okay, so here's what I'm thinking, guys. I'm thinking there's a pattern there. I bet I could factor that pretty easily by grouping, factor by grouping. But I kind of have lost track of where am I in terms of depressed polynomial anyway. Okay, so I started, remember, with, when I started using synthetic division, this guy was x to the 5th. This guy got me down to x to the 4th, and then this guy will be x to the 3rd. Let's take a look at what I'm left with here for a depressed polynomial. I have x to the 3rd plus 2x squared plus 1x plus 2. I'm going to break this into 2 groups because there are 4 terms. Out of the first group, I can factor out an x squared, and I'm left with x plus 2. Out of the second group, I can factor out a 1. and I'm left with x plus 2. And I know I am doing a smashingly good job here because I have the same factor in both groups, that same factor of x plus 2. So, ta-da, it factors, and then, you know, using the zero product property, set it equal to 0. X is equal to negative 2. X squared is equal to negative 1. Square root. X is equal to plus or minus, the square root of negative 1 is I. Okay, so let's take a look at the big picture here. I think I'm done. I've completely factored everything. The cool thing is the fundamental theorem of algebra says that if you have an nth degree polynomial, you're going to have n roots. I needed to have 5 roots. And the fundamental theorem of algebra just says that those roots can be multiples, they can be complex, of course they could be real. All right, well, how many did I come up with? Here's one, here's one, here's one, and then there are 2 more. 1, 2, 3, 4, 5. I have 3 real roots. X is equal to 1, 2, and negative 2. And then I have, of course, 2 complex. Just remember the complex root theorem or conjugate root theorem from the other day. Another important theorem, and at that time it was the most important theorem. Today is just one of our theorems. The conjugate root theorem says that if you have complex roots, they're going to show up in pairs. And they sure did. I ended up with I and negative I. All right, so that's the fundamental theorem of algebra. Super cool.